So I'm very happy. I'm very excited to be here. So I'm going to be talking about fully nonlinear elliptic equations, which is another subject that is very appreciated by Luis. So I'm going to tell you what they are and some ramifications of the theory. So let me start going back to something that Sylvia started to explain today, which is how to relate an elliptic partial differential equation, how to derive it from a random walk problem. So let's start from a discrete problem. So here I have a city, the scheme, like some simple city, that each one of these is a block, and we have a disoriented tourist that is at any, whenever he gets to any corner, he picks one of the 4 directions at random and walks in that direction, right, with equal probability. So we want to compute the probability that this tourist will get to the beach before going to any other point on the boundary of the city, right? And this probability depends, of course, on the initial point where this person starts this random walk, right? So how would we compute this probability, right? So it's something that gives us a discrete equation relating the values of this probability depending on each one of those points, on those vertices of the city, right? And the way to do it is the following. If we say this function u, depending on the point x, is this probability, then the value at any point should be equal to the average values of the same function on the neighbors, because after one step, this person will be in any of the 4 neighboring points with equal probability, right? So after that one step, we don't know in which of those 4 is going to be, but the probability, let's say, after moving one step to the right, will be u at x2. If we start at x, we're going to move to one of those 4 with probability 1/4. So the probability at x is the average of the probabilities of any of the 4 neighbors, okay, of reaching the beach from any of the 4 neighbors. So we get this discrete equation that relates the values of u at any one of the corners of the city. And if we move terms around just by, this equation, put the 4 there and subtract it, we can rewrite the equation in this particular form. And when you rewrite it like that, you realize that the equation is showing second-order incremental coefficients in the horizontal direction and in the vertical direction for the function u. So here we have the values at the right and left, minus twice the value at the center. That's what we have here, which is a discrete version of the second derivative in the horizontal direction. And the other one is a discrete version of the second derivative in the vertical direction. So what we see is a discretized Laplacian from this random walk. If we look at this random walk problem and we think of a very large city that has many, many, many blocks, or perhaps, we take the size of this block to go to 0, then the variable x will become a continuous variable, right? The random walk will start to look like a Brownian motion. This is a very lousy picture of a Brownian motion, by the way, and in reality it looks much more complicated. But anyway, you get the idea. So the discrete equation that I wrote before, when you pass to a continuous variable, becomes the Laplace equation, right? And this is some way you can relate this random walk problem to the Laplace equation with some boundary condition. And for the beach problem, it would be the function u is 1 on this side of the square and 0 on the other 3 sides of the square, right? That's once the random walk reaches the boundary, then you know what the value of the probability is. It's either 1 if it reaches the beach, or 0 if it went in the wrong direction. All right, so now let's introduce some preferences to this random walk. So let's say that this random walk is more likely to go in the horizontal direction than on the vertical direction. It says whenever you are at the corner, this person will be twice more likely to move horizontally than it is to move vertically. Then when you do the averages, instead of having a plain average of the 4 neighbors, we will have a weighted average where some of the points have a larger coefficient than the other, right? And when we take the continuous limit, instead of getting the Laplacian, we will get the Laplacian with some coefficients. So this is an elliptic equation with coefficients. Here I have twice the second derivative with respect to x plus the second derivative with respect to y. right? So a random walk with preferences that some directions are chosen more often than other directions gives us an elliptic equation with coefficients, right? So this is how we get the Laplace equation and how we get linear elliptic equations with coefficients. Now, how would we get a nonlinear equation from a problem in random walks? So this happens when we want to take a control problem or we take a problem in optimal design. So to keep the example of the city in mind, imagine that for whatever reason, some directions look more appealing than the other, and we want to design a city so that the tourist is more likely to end up on the beach, maybe because we have an ice cream store at the beach and we want them to buy it, right? So if the only choice that we have is to somehow manipulate these probabilities so that every corner, either the horizontal or the vertical direction is going to be chosen twice as often as the other, right? Then if we want to solve the problem in which not only we want to compute this probability, but we want to compute the optimal way to decide design these preferences at every corner that gives us the largest possible probability. And then the equation, instead of being U being the weighted average, because I don't know which of the two choices I'm going to take, is going to be the maximum between the two possible choices of weighted average. And that's going to be our equation at every corner of the city, right? So it's our discretized equation now became a nonlinear equation because it's a maximum of two linear functions. When we pass to the continuous limit, that would be the problem when have a very, very large discretization of a city, then we get a maximum between two linear elliptic operators that is equal to 0. So this story that I told you about the city with the probability in the horizontal direction being twice as much on the vertical or the opposite could be retold in many different ways, in many different contexts, in which you have random walks and stochastic processes that have preferences to moving in one direction over the other, and we can somehow manipulate those preferences and try to optimize for for the best expected value of certain outcome function. And then this comes with the name of the Hamilton-Jacobi-Bellman equation. We have an equation, a nonlinear equation of the Hessian that holds at every point, which is the supremum of linear elliptic equations. So there is a family of linear elliptic equations parameterized by this parameter alpha, and we would take the supremum over all the alphas, and that's the equation that our optimal configuration will satisfy. So there is a boundary condition, and there is this nonlinear equation that satisfies in the interior of some domain. So like I said, this is the problem that we get when we look at the supremum of all possible controls alpha of the expected value of the boundary value of a function, which corresponds to the moment that a diffusion stochastic process hits the boundary. I notice that any convex function is a supremum of linear functions. So basically, this derivation of an equation would work for any convex function of the Hessian, provided that I want all these coefficients to be positive matrices. I think that's going to be written there. So there is a condition that if the derivative of f is a positive definite matrix at every point, and f is a convex function, then the equation f of d squared of u equal to 0 can be derived by some of these problems of stochastic optimal control. There is also a possibility of building two-player stochastic games to derive an equation when f is not convex. That comes from interaction of two controls where one player wants to maximize an expectation and the other player wants to minimize an expectation. But the one thing that will always be true for any of these problems in stochastic games and stochastic controls is that the equation will be uniformly elliptic. The probabilities of moving in any direction are always non-negative numbers, And that translates into the fact that the derivatives of this function f with respect to the matrix will always be a positive definite matrix. And I'm going to write it in this way, the ellipticity condition. So there is something called uniform ellipticity, which is a crucial condition to get regularity of fully nonlinear elliptic equations. So the uniform ellipticity condition is, well, in the previous statement, it would correspond to the fact that of the eigenvalues of this matrix being uniformly bounded from below and above. In terms of when you have a given nonlinear function of the Hessian, one simple way to express it is that if you evaluate the function at a symmetric matrix A, and now you add a positive definite matrix B, then the difference of f at those two matrices is controlled by below and above by a multiple of the trace of the matrix B. You see that if f was just the trace of the matrix, then f of d square of u would be the Laplacian, right? The Laplacian is the trace of the Hessian. So if f was the Laplacian, the little lambda and the capital lambda would be both equal to 1, right? The uniform ellipticity is quantifying, in a way, the comparability of the increments for your nonlinear equation with what you get for the Laplacian, all right? So the fully nonlinear elliptic equations in the 70s were a very poorly understood subject. But then at the beginning of the 1980s, there were some breakthrough developments that improved our understanding of the subject. And it started with some a priori estimates over solutions that were initially, the first result was by Krylov and Safonov. It was announced in 1979. The final paper is published in 1980. That they provided control of Helder-Modulus continuity of the derivative of a solution in terms of the maximum of the value of the solution u, right? So an a priori estimate is you have a solution of an equation, and you want to have an upper bound of certain quantity related to the solution in terms of some other quantity. You see, this is, of course, an inequality that would not be true for any function at all. If you have any given function that doesn't satisfy any equation in particular, you can never say that the derivative is, the maximum value of the derivative is bounded by the maximum value of the function, by a constant. But if it is a solution of an elliptic equation, they could prove that. If it's a solution for a uniformly elliptic equation. If you add the convexity assumption, then you can get an upper bound on the Helder norm of the second derivative of the function. And that's a theorem that was proved independently by Evans and Krylov, also by the beginning of the 1980s. These were initially a priori estimates on strong solutions, because at that time, we didn't know a proper notion of solution for fully nonlinear elliptic equations. You know, if I want to talk about, if we're talking about singular solutions, if we're talking about what's the regularity of solutions, that means that we have to have a notion for saying what the solution is for a function for which the second derivatives cannot be computed, right? And that was not properly understood at the beginning of the 1980s, right? So these were initially a priori estimates for strong solutions, for solutions whose second derivatives are well defined. So shortly after, there was the notion of viscosity solutions that was derived. Initially, it was a concept that was developed for the study of the Hamilton-Jacobi equation by Crandall and Lyons. So the Hamilton-Jacobi equation is a first-order equation, and they were approximating it by adding an extra viscosity term and making it go to 0. And then they had a definition of what this generalized notion of solutions was. And the definition can be applied to second-order elliptic equations as well. But it was not initially clear if that notion of viscosity solution was going to give you a unique solution in the context of second-order equations. Because when you write a generalized notion of solution, what you're doing is you're weakening the requirements for a function to satisfy an equation. But if you weaken the requirements too much, it may happen that you have more than one solution of the same equation. And that was, so Bob Jensen proved in 1988 that there was only one solution. So I'm going to give you the definition of a viscosity solution in the next slide. So basically, when you have a full nonlinear elliptic equation with any boundary condition, it can be proven that there exists a unique viscosity solution. However, this viscosity solution is just a continuous function a priori. Neither the first derivatives or the second derivatives have to be well defined for you to be able to say that the function satisfies the equation. All right? Let me tell you what the definition of viscosity solution is, so you get the idea. If you have a continuous function u, you could say that the function satisfies the inequality f of d squared of u greater or equal than 0 if whenever there is a smooth function that is tangent to u at any given point x0, then that smooth function satisfies the inequality at that point x0, right? So you should be able to see that if u is a classical solution of an elliptic equation, then this condition should be satisfied. If phi is tangent to u from above, then the Hessian of phi should be greater or equal than the Hessian of u at that point x0. The monotonicity, the ellipticity condition of f tells you that f of d squared of phi has to be larger than f of d squared of u at that point. So by making the definition of the f of d squared of u greater or equal than 0 to be that this happens whenever a function like this can be found, then you are transferring the requirement on regularity from the function u to the test function phi, right? So you can verify whether this condition holds or not for functions u that don't have to be smooth, that don't have to have well-defined second derivatives, that are just continuous functions. But by making this a definition, you're also running into the danger that there may be very few points where the function u can be touched from above and from below by a smooth function. So if your function u is very, 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 very irregular, it may happen that the points x0 where you can find a test function that touches from above or below are a very small set. So you could think that a condition like this is maybe allowing a lot of very irregular functions to be solutions of the equation, because the requirement of what you're imposing an irregular function to satisfy is, in a way, easier to satisfy the more irregular the function is, because there are fewer points where you can find a test function. So by making this definition of viscosity solution, it may be that full nonlinear elliptic equations may have solutions that are continuous functions and are not any smoother than that. So then the question is that really the case? Or are the solutions going to be smooth? Or are the solutions of full nonlinear equations going to be C1? Are the solutions of a full nonlinear equation be C2? Or what are they going to be? Okay? All right, so here is a theorem by Luis Caffarelli on the regularity of solutions of full nonlinear elliptic equations. And so the theorem, it was a very comprehensive result that came in one single paper, and it was it's about equations that are x-dependent and have a right-hand side, and it gives conditions on the equation that would give different levels of regularity for the solution. So the first one says that when f is uniformly elliptic, and it's the oscillation with respect to x of the equation is locally small, but in particular it could be true whenever you have continuity with respect to x and for the equation on the right-hand side. Then the function u, the viscosity solution of the function, which a priori was just a continuous function, turns out to be differentiable, and the derivative will be Helder continuous. The second condition is that the second result is that if you have a uniform elliptic equation and it's also convex, then the solution has to be second order differentiable, twice differentiable, and it's going to be the second derivative is going to be Helder continuous. And the third one is on the W2P regularity for solutions to uniformly elliptic and convex solutions when the right-hand side is in LP. It's only in LP. So the proof of this, of course, uses some ideas of the a priori estimates that I mentioned before, and introduces a lot of new ideas, very geometrical ideas about the understanding of how to get this type of regularity. Very importantly, it introduces a method that is very effective about how to deal with equations that have x dependence. That is not so. Here the equation depends on x, and so we have a different equation at every point that is changing with certain assumptions of continuity, and it provides a very effective method on how to deal with variable coefficient equations, to a point that the result was new even in the linear case. So it was introducing some improvement even for linear equations. So the way that Luis described the result was by the freezing coefficient method. So it was, you have an equation with variable coefficients, so the equation is different from point to point, but the equation is similar. There are some estimates on how the equation changes from point to point. So you want to compare the solutions of your equation with the solution of the equation that will have constant coefficients. They will have like frozen coefficients at the center point of the ball. So this perturbative theory that quantifies how much your equation changes locally from the constant coefficient equation to the variable coefficient equation, and it uses that very effectively to get good regularity results. And let me tell you that all the theory and all the methods are very geometrical in the sense that they are, well, you know that it has to start from building the right test functions to compare from below and above by having a good geometrical understanding of what the regularity conditions mean. For example, here I have the W2P result. If you start from a function that is continuous, and you want to prove that the function is in W2P, and you're only going to use that you have tangent smooth functions from one side and the other, then you have to restate what it means for a function to have a second derivative in LP by the type of openings that the paraboloids that are tangent from above and tangent from below can have. So it's like you have to give a bound on the measure of the set where you can touch from above and from below with parabolas of certain opening. So there is a geometrical re-understanding of what it means for a function to be in W2P. And the same could be said about any of the other results. So anyway, this is a very important result for the regularity of solutions for fully nonlinear elliptic equations. As I said, it was published in a paper in 1989. But however, if you want to read about this today, the standard place that everyone reads it is in the book that Luis wrote with Xavi Cabré. That is a book on fully nonlinear elliptic equations that is very popular. So one particular fully nonlinear equation that Luis was very interested in, and he worked a lot on, is the Monch-Ampere equation. So one of the things about the theory of elliptic equations is that you very rarely can apply off-the-shelf result. Even if the previous result about fully nonlinear elliptic equation sounded very general, when you want to go and apply to a particular equation, you always come up with difficulties. So this is a fully nonlinear elliptic equation, which my f of d square of u, the equation the function that we're applying to the Hessian of u is the determinant. So we prescribe the determinant of d square of u at every point. Here u is expected to be a convex function, so the Hessian is a positive definite matrix, and we want to prescribe its determinant at every point. All right? So this equation is not exactly uniformly elliptic. The equation is well behaved when the eigenvalues of the Hessian are bounded below and above. But the equation will degenerate, the ellipticity of the equation will degenerate when one of the eigenvalues of the Hessian becomes very close to 0. So that adds, of course, completely different, new type of difficulty compared to the general uniformly elliptic case. And in a series of papers by Luis Caffarelli at the beginning of the 90s, he found conditions to prove that the viscosity solutions, which is equivalent to another concept of weak solution for Monchampère by Alexandrov, that the regularity of the viscosity solutions for the Monchampère equation is C1 alpha, C2 alpha, or W2P, with different conditions on the function f. So this is for strictly convex solutions of the Monchampère equation, and that's the regularity theory that we know for the Monchampère equation. The Monchampère equation has two canonical applications. One is to study surfaces with prescribed Gaussian curvature. That would be, it gives you the same as the Monchampère equation with some first-order correction. And another one is the problem in optimal transportation. So let me tell you what the optimal transportation problem is about. So the optimal transportation problem is you have two measures, and you want to find a way you want to find an optimal transport map that pushes one measure into the other and minimizing the transportation cost. So imagine that you have a pile of sand, and you want to transport it into a sandcastle, and you want to find a way to transport the pile of sand in the most efficient way. So if you have a quadratic cost, let's say that the cost from transporting something from point X to point T of X is like the distance between those 2 points squared. If you have a pile of sand here and a pile of sand here, and you want to transport it to a pile of sand here and pile of sand here, you should take the one that is closer here and the other one there, because otherwise the sum of the squares is going to be larger. So the optimal transportation cost is looking for this way to transport a measure into another one in the cheapest possible way. So you look at that and you say, what is the Monchampère equation? What is the PDE? So that's related to a result of Brownian that says that when your two measures are absolutely continuous, so they have a density function f and a density function g, then the optimal transport cost is the gradient of a convex function. Turns out to be a gradient of a convex function. And if the optimal transport cost is the gradient of a convex function, then the Jacobian of that gradient, of that change of variables, has to be the ratio between f and g, right? At the point x and at the point t of x. So we get that the determinant of d squared of u, which is the Jacobian of the gradient of u, is given by that ratio. So the Monchampère equation is obtained from the optimal transportation problem. Well, if g was a constant function, we will get the simple Monchampère equation. Otherwise, we get the Monchampère equation with some first-order correction. So the optimal transport problem has been a very active area of mathematics since, I didn't write the year of this. This is mid-80s, right? Yeah. Mid-80s, right? Well, so I think 94 is the other one, the one by McCann. Well, yeah, so sometime around 1990, maybe late 80s. 87, we say 87, well, yeah, so around that time. So, but since this result, optimal transport problem has been a very active area of research. So the regularity theory that was developed by Caffarelli at the beginning of the 90s in this series of papers, of course, plays a very important role in the study of optimal transportation. So now I'm going to jump to a different type of problems, which is the fully nonlinear elliptic equations that come from non-local problems, from interdifferential equations. So I want to tell you, I want to go back to the random walk derivation of an equation, but I'm going to do it a little bit differently. So now I'm going to start with a point in a domain, and in every time step, I'm going to choose a point at distance less than 1 from wherever I am with uniform distribution. So I'm going to take a ball, radius 1, center at the point, and I'm going to take my next point is going to be any point in that ball. So maybe that's going to be my next point in my random walk, right? And then we take another ball centered at wherever I am, and I choose my next point uniformly among any point on that ball. And that's where I end up. And we're going to keep going until the process exits the domain. OK? Now, we define the function u of x, x is the initial point, as the expected value of some given function f at the first point that we exit this domain, right? So if we want to see what equation the function u satisfies, then we have that outside of the domain is not the random walk is not going to move at all. So outside of the domain, u of x is equal to f of x, right? But inside of the domain, we have this integral equation that says that the value at any point x has to be equal to the average values of u at any point in the ball of radius 1 centered at x, right? This is an equation that was in the slides written by in Luis's slides this morning, right? Completely coincidentally, because we didn't talk to each other. But it's the same equation, right? So when you take this simple random walk, we derive this integral differential equation. And this equation is somewhat a non-infinitesimal version of the Laplacian. Why is that? Because the Laplacian, there are different ways to understand what the Laplacian is. The most boring of all ways to understand the Laplacian is that the sum of the second derivatives in all the possible coordinates, right? Which doesn't tell me anything. Then you can think about the Laplacian as the divergence of the gradient, that if you understand what divergence and gradient means, it might have some meaning. And the third way, which is what is most relevant right now, is that if you take the average of the values of u in the ball of radius r centered at x, and you subtract the value of u at x, and you divide by the power of r that gives you a non-trivial limit, then that's exactly the Laplacian as r, the limit as r goes to 0 will give you the Laplacian. So the Laplacian measures infinitesimally how much the average values of u in a ball, in a tiny ball centered at x, deviate from the value of x. So if the function is curving up, you're going to have a positive Laplacian, because around the point x, the values of u are going to be a little bit higher. If the function is curving down, you're going to have a negative Laplacian. Typically, you have a function that in some direction curves up, in some direction it curves down. I think I did the opposite side. In some direction it curves up, in some direction it curves down. And the Laplacian averages all those deviations from the average in the ball of radius r. So when we study an equation like this that comes from this random walk problem that I described before, what we have is we're not really taking that limit as r goes to 0. We are stopping before taking that limit. And we are looking at a non-infinitesimal version of the Laplacian, and we can still write an equation for it before going to the limit. So maybe we can say that the Laplacian equation, and maybe the whole theory of elliptic equation, is a limit case, is an extremal case of this more general family of equations that are integral differential equations that is before you go to the infinitesimal limit. So all these integral equations already satisfy a lot of the properties that the Laplace equation satisfy and the elliptic equation satisfy, because this equation already satisfies that for any boundary value, so for any, there was a function f that was equal to u outside of omega, there exists a unique solution. So we have existence and uniqueness. The maximum principle holds the value of the solution u. The maximum solution u will be smaller or equal than the maximum of its boundary value f. And perhaps we can prove some regularity of results for solutions of integral differential equations. So integral differential equations are equations that share a lot of the properties that typical elliptic theory has, right? And you can say this is really what it's a very rich family of equations. There's a huge number of equations you can think of, and the second-order elliptic equations are like a limit case of this. So what I want to do is, instead of looking, of course, this is a very simple example, but we may think about a similar equation where instead of taking the average values on a ball of radius 1, we weight that average by any kernel function that is any non-negative kernel function. So one particular one that I think I wrote in the wrong sign, it was correct in Sylvia's slide this morning, so this should be ux minus uy. When you take the fractional Laplacian, it corresponds to an integral differential operator with the kernel y minus x to some negative power. So the fractional Laplacian is this operator that, when you look at the Fourier transform of a function, corresponds to the Fourier multiplier xi to the 2s. When s is 1, is the regular Laplacian. When s is between 0 and 1, it corresponds to these integral differential operators. So the fractional Laplacian is going to play the role of the Laplacian, the same role that the Laplacian plays for elliptic equations. The fractional Laplacian is going to play for integral differential equations of fractional order. So a uniformly elliptic equation was an equation that has some increments that were comparable to the Laplace operator. Here, an integral differential equation that is elliptic of order 2s will have to be comparable somehow with the fractional Laplacian of order 2s. So this would be the Bellman problem for an integral differential equation. So when we were talking about this random walks with preferences and this optimal design problem that leads us to the Bellman equation, we ended up with an equation that was the maximum over linear elliptic operators. We can also think of a maximum over linear integral differential operators if we are studying the same problem, but our random walk, instead of being a standard diffusion process, it is a jump process where the kernels k sub alpha are different preferences and different frequencies of jumping in different directions. Our parameter alpha is giving us a control, and we want to control this process in the way to maximize the outcome of the problem, to get the largest possible solution for some given boundary value. And then that leads naturally to this problem. That is the maximum of a family of linear integral differential operators is equal to 0 for every value of x inside the domain. So what would be the ellipticity condition? I would want every one of these kernels to be in some way comparable to the kernel of the fractional Laplacian. Comparability could be that it's bounded below and above by a constant times the kernel of the fractional Laplacian, right? Which would be h to the minus d minus 2s. So a theorem that I have with Luis Caffarelli is that this non-local Bellman equation has a solution that is going to be regular of order a little bit more than 2s. So this is actually a non-local version of the theorem of Evans and Krylov. The theorem of Evans and Krylov says that a solution to a convex uniformly elliptic equation is C2 alpha. Has the second derivative is Helder continuous of order alpha. Or in other words, the regularity of the solution is a little bit more than C2, a little bit more than 2 derivatives. Here, the order of the equation is 2s. And what we have is that the regularity of the solution is a little bit more than the order of the equation, right? And this is enough, in fact, to make sense of the left-hand side, or make sense of the operator classically. So in a way, it says that the solution to the convex integral differential equations don't have to be viscosity solutions. They're going to be classical solutions, right? So this is the result that we have with Luis. All right. And like I said, the non-local equation theory has also been a very active area of math for the last 20 years. There is a lot of problems to think about in non-local equations because there's a very rich family of equations. There is the fact that at every point you are making an equation that involves kernels, which is, gives you a lot more flexibility and degrees of freedom than looking at a matrix of coefficients, means that the world of integral differential equations has a lot of possibilities and things to study. And there is existence and uniqueness solution results, comparison principle, regularization effects, Harnack inequality, regularity results. There is a lot of things that people have developed in the last couple of decades about integral differential equations. So I want to finish by describing some application, which is not by Luis, which is to the Boltzmann equation. So the Boltzmann equation is an equation that describes the evolution of the density of particles in a dilute gas, right? So we have a function f that depends on time that tells us let's say the probability distribution of finding a particle at position x and velocity v. And it's an equation that the left-hand side is the transport equation. The particles travel with velocity v, but the particles interact by the right-hand side of the equation that is a complicated integral operator. And this is an equation that comes from statistical mechanics. There is also a very active community that has been active for many years studying the Boltzmann equation. And the first time, this is an equation, this is not the topic that Luis has studied, but the topic that I learned from Irene, in fact, because that's what Irene works on. And I learned, she teaches the graduate class on the Boltzmann equation in the UTOSIN that I took. When you look at this, it doesn't look elliptic at all. I mean, it doesn't look even like a PDE. It's like an integral operator here. But when we study non-local equations with Luis, we were studying integral differential diffusions. This doesn't quite look like the one I mentioned before. So when it's what we have, but in fact, if you start working with this operator, you can discover that inside this operator there is some elliptic integral differential diffusion hidden, right? Well, when you study nonlinear equations, the nonlinear equations, nonlinear elliptic equations, you have to, I was saying before when I was talking about the Monch-Ampere equation as a fully nonlinear elliptic equation, you cannot really apply off-the-shelf theorems, general theorems from elliptic theory and apply them to your equation and get the results right away. Here, you cannot apply right away the theorems that we had for non-local integral differential equations into these equations. But we could use all the techniques that we developed with Luis Caffarelli and all the ideas that Luis developed for regularity theory for elliptic equations and for non-local equations into this equation. And I have a result with Cyril that says that the solution of the Boltzmann equation are C-infinity smooth, provided that the mass density, the energy density, and the entropy density are bounded and away from vacuum. So this is a conditional result. This is something that says that if macroscopically our density of particles is looking fine, then the solution at the microscopic level has to be C-infinity. So the point is that the techniques for regularity of non-local equations that Luis developed can be applied in problems that are very diverse to what they were originally intended for, right? So here the main ideas driving the proof are the ideas that Luis worked on for fully nonlinear equations, and later we also worked on for integral differential equations, right? So in the Boltzmann equation, it shows in this theorem, right, which is a subject that he never worked on, but his ideas will have influence in this other subject in the same way that in many other subjects, these ideas for regularity are going to have an influence. All right? And I think this is the last thing I had to show.